Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing step-up choppers. And here is a step-up chopper. Why we call it a step-up? Since the output voltage is greater when compared to that of the supply voltage which we are actually providing. So that is the reason we call it as step-up chopper. And here, if you see, we are making use of an inductor, and this inductor is connected in series with the supply voltage, and this combination is connected in parallel with the transistor. And here we are also making use of a diode, and this diode is connected in order to avoid the current flow right from load to source. So in order to avoid the current flow from load to source, here we are connecting a diode, and here we are also making use of a capacitor in order to provide the output voltage smooth as well as a smooth output current. So that is the only reason why we are actually making use of a capacitor over here. And now let us observe the waveforms. Here the moment when we provided the base drive, for the transistor, that is right from the instant 0 to delta t, here we have provided the base drive. So that means the moment when we provided the base drive, transistor is actually conducting current. And if you see, current is flowing through supply, inductor, transistor and back to supply. And this is the individual circuit diagram when the transistor is on. And if you see the voltage across the transistor, see the on state voltage across the transistor will be, any device, electronic device will be very low, and it will be equal to that of the on state voltage drop of that particular device, which is very less, and it is almost considered as zero. So that is the only reason from 0 to delta t, the voltage across the transistor is almost considered as zero, that is on state voltage. And the moment when we withdraw the base drive right from this instant 0 to delta t to t, we have withdrawn the base drive. That means the transistor is turned off. When the transistor is turned off, the whatever the supply voltage which we are actually feeding will be appeared across the transistor. So that is the reason right from delta t to t, that is during the off state of the device, the supply voltage will be appeared across the load, and this will be of the magnitude Vs. And this is nothing but the voltage across the transistor. We are purely here talking only about the voltage across the transistor. And again at this instant called t, we have provided the base drive for the transistor. Right from t to t plus delta t, we have provided the base drive, and that is how since the on state voltage drop of the device is very less, it is almost considered as zero. And again at this instant called t plus delta t, we have withdrawn the base drive. That is how supply voltage will be appeared across the transistor, and that is how we are getting the output voltage from t plus delta t to 2t. So this is all about the voltage across the transistor. Hope you understood my point. When it is on, the on state voltage of the device is very less, it is almost considered as zero. And the moment when we withdraw the base drive, because it is in the off condition, the voltage, supply voltage will be appeared across the load, and that is how we are getting the voltage across the transistor right from the instant delta t to t with magnitude Vs. And now talking about the current across the inductor or supply current. Why current across the inductor or supply current? Both are one and the same. If you see, the supply current is what is flowing through the inductor as well. That means Is is equal to IL. Both are one and the same. So exclusively this is the current which is flowing through the inductor or supply current. And here we are getting the supply current right from this instant called I minimum to I maximum. We are getting the current flow through the inductor. As long as transistor is remained on, since it is driving the current through the inductor, that is how we are getting the current flow through the inductor. And you already know, inductor, it does not allow any sudden changes in the current. So that is the reason current is building at a slow rate, and it is becoming maximum at this instant called delta t, and the moment it reaches delta t, we have withdrawn the base drive. And since we have withdrawn the base drive, again whatever the energy stored in the inductor, it will be whatever the voltage across the inductor, that is VL is equal to L into DIL by dt. This voltage will be maintaining diode in forward biased condition, and that is how the diode is forward biased because of the voltage across the inductor, and that is how this diode is driving the current through the load. When the transistor is remained off, since it is acting as an open switch during the instant called 0 to delta t, when the transistor was on, inductor has stored certain amount of energy, and when the transistor is off, this diode is getting forward biased, and this is what driving the current through the load. Whatever the energy stored in the inductor is dissipated through the load, and while energy is provided by the inductor, the current through the inductor is getting reduced, and before even it becomes 0, again at this instant called t, from t to t plus delta t, here we are providing the base drive for the transistor. So that is how again transistor came into the picture, and it is conducting, and when transistor is conducting, energy is being stored in the inductor. And if you see, this is the current flow through the inductor right from t to t plus delta t, it is rising, and the moment it reaches t plus delta t, since we have withdrawn the base drive, whatever the energy stored in the inductor is what driving the current through the load. Since it is providing the energy stored in the inductor is getting depleted, so that is how the current through the inductor is getting reduced. So this is purely current waveform across the inductor. So supply current or current through the inductor is one and the same. And now, if you observe the waveforms across V0 average as well as I0 average, it is almost continuous and ripple free. And if you observe, output voltage is greater when compared to that of supply voltage as well. Okay, how could we achieve this? How the output voltage is even more greater when compared to that of the supply voltage? That is because here we are taking V0 is equal to supply voltage plus L into di0 by dt. That means output voltage, this is the combination of supply voltage as well as voltage across the inductor. The voltage across the inductor is adding on to the supply voltage which we are actually feeding. So that is the reason the summation of supply voltage as well as voltage across the inductor is nothing but the net voltage across the output voltage which we are actually getting. So that is how we are obtaining output voltage greater when compared to that of supply voltage. Hope you understood my point. And here, and if you see, when transistor is on, when this inductor voltage, if you see, inductor voltage is added to that of the supply voltage, and the combination of these both is what appeared across the load, and that is how we are getting the output voltage which is greater when compared to that of the supply voltage. That means this is acting as a step-up chopper now, and apart from that, whatever the voltage which is applied across the load, this capacitor tends to charge to that particular boosted voltage, and that is how when the transistor is on, when the transistor is on and it is conducting current through the inductor, the capacitor which was actually charged will be driving the current through the load. And when the transistor is turned off, at that instant, whatever the energy stored in the inductor, forward bias is diode and it is driving the current through the load. And at this instant, capacitor gets charged, and when transistor is on, it is providing the continuity of the current flow. That is how we are getting the continuous and ripple free current waveform, as well as supply voltage. If you see this this output voltage is greater when compared to that of the supply voltage because of the addition of the voltage across the inductor, that is L into di naught by dt. That is all about the step-up chopper. Now, use of step-up chopper for energy transfer. Usually, step-up chopper is normally used in DC drives, and this is used for energy transfer purpose. And here if you see, this is a fixed or variable source, and from fixed or variable source, here we are feeding the energy back to the DC supply. And step-up chopper is normally used in DC drives, and supply voltage let this particular supply voltage be the back EMF of the motor, and this back EMF of the motor, it purely depends upon the speed of the motor, and this is actually fed back to the supply, and we call this process as regenerative braking. Here the power is not wasted, rather it is fed back to source. The power is not wasted, rather it is fed back to source. See, normally here when the transistor is on, the inductor is getting charged, and once the transistor is off, whatever the energy stored in this particular back EMF of the motor is fed back to the supply through this particular diode. Until whatever the energy stored in the inductor, it is forward biasing the diode, and it is driving the current to the supply. I mean, the current is fed back from the load to source, and this process we call it as regeneration. Let us assume this is the back EMF of the motor, and when the speed of the motor is less, at that instant when we are applying the brake to a motor, so whatever the energy stored in the back EMF will be actually fed back to the supply. So that is all. Here this particular step-up chopper used in DC drives will be usually used for energy transfer purpose. That is, from energy is transferred right from back EMF of the motor to the supply. So here power is not actually wasted. Let me give you a practical example. When the train is traveling down the hill, in that case we usually the speed will be getting reduced, and the speed will be getting reduced from the larger value of the speed. The speed which is required will be usually less. So whatever the energy stored in this particular back EMF of the motor will be supplied right back to the supply. So here energy is not actually wasted, rather it is fed back to source. So that is how that is a practical application of this step-up chopper, and it is usually used for energy transfer purposes. And in the coming up lecture, we'll be seeing classification of choppers. Thank you.